Maulana Abul Kalam Azad University and Technology, West Bengal, and the Islamic University of Science and Technology. Now, in our inauguration, our Honorable Vice Chancellor, Sir, Professor Shokit Matra here joined, and we are having the three invited speakers: Dr. Ashish Kundu, IBM TJ Watson Research Center, USA; Dr. Kirill
Dr. Giri, you are not audible.
Dr.
Giri sir, please continue, sir.
Continue.
Okay.
Dr.
Okay,
Ashish
sir,
Kundu,
now we
Dr.
request to
Giri,
our Honorable Vice Chancellor.
Yes.
Okay.
Thank you, Doctor. Thank you, Dr. Giri. Can you hear me properly? Because I can see there is
yes, sir. Can you speak?
Yeah, I can continue, but I have seen there are certain these reports on audio disturbances. However, this is this as Dr. Giri reported. This is the seventh in the series of the webinars on cryptography, network security, data security, and it's a great endeavor from this Department of Information Technology under the stewardship of Dr. Devashish Giri and other faculty members, Dr. Somdatta Chakraborty and others from this department. And this is one of the great things, as I tell it at every occasion, at the pandemic scenario. Maybe this you can consider as something, this blessing in disguise, as we are continuing all our activities in digital platform. And from the very beginning, when this pandemic scenario started at this country, we embraced this technology, we embraced this culture at the quickest possible time. The outcome of it is now large numbers of programs, training programs, webinars, workshops, all these are happening at digital platforms. And here, one of the beauty of this thing is that resource persons from different parts of the world, they could attend this program, they could join these programs for sharing their experience, for sharing their knowledges, for sharing this expertise with for our learning communities, and that is the great thing. So at this particular time, we could break these boundaries of space, boundary of time, boundary of numbers, because otherwise it would have not been possible within a short period of time to organize these types of international, these programs. International webinars is always, this worldwide web, which is it breaks the boundary of national or international. So normal time, it would not be possible to organize these types of international seminars. This guy inviting persons from different institutes, universities from different parts of the world. This is one of the unique things. And we are very happy that our university has taken all steps in taking the benefit of, in reaping the benefit of this particular scenario. Second is, this area is of tremendous importance, as everything is happening at digital platforms, and otherwise also the world was moving towards a new form of this format where manufacturing, service, education, entertainment, financial transactions, all of these things, they those have been started. The practices have been started in digital platforms and digital domain, and therefore the security of data is of immense importance, because as these activities, most of the things are happening on digital platforms. So organization wise, individual wise, country wise, we need to protect this data, we need to secure this data. Therefore, network security, cyber security, data security, all these things are of tremendous importance, and we need to develop a large numbers of professionals who can safeguard all these things for the for not only for individual these human beings, but also for country and also for the entire world. And for that purpose, we need to have more short training programs, for in these directions for generating this appropriate knowledge community. And in this webinar format, we have introduced discussion forum, where the thing is that those who are participating, they can share their opinions and views, and that can result in further generation of knowledges. And that is that knowledge generation is of this tremendous importance in this context, because these new ideas, innovative ideas, imaginative ideas, that you can validate, you can test, and you can with all your peers. And that is one of the things. Secondly, as all of these things we are organizing in these digital platforms, we are keeping a record of all these things. Everything has been properly recorded, and that are this available with us, all the resources available with us. So any member of this learning community at any point of time, they can access all this repository and all these things. I think these are being uploaded to social media for the benefits of a larger section of the society. So these are great things from our side, and I'm very happy and very proud that all our faculty members, our staff members, our researchers, they have taken a lot of efforts in making it happen, in making it a reality. And with this, I wish this very happy, effective, and successful learning to the knowledge community or learning community who are present over here. My sincerest thanks to the resource persons. I can say Dr. Kirill Morozov, Dr. Georgia Azazur, and Dr. Ashish Kundu. They from different organizations. They will be sharing their experiences with our participants, and this will be a great help to, in validating or in understanding the new concept in this area, tools, techniques, methodologies, all these things which are being followed in the field of cybersecurity, data security, network security. I always give emphasis on one particular aspect, that this is the time where self-learning or aptitude towards learning is very, very important. So whatever we will be learning from here, this is important, but more important is we should take it forward. Whatever we are learning, we need to further augment it or upgrade it or supplement it from knowledge resources which are available at digital platforms. Numbers of online courses available at OpenCoursewares, MOOCs, and other platforms. So my request to all the participants is kindly look into it and upgrade your knowledge further. And we believe that all of you have the potential to nurture this area further for growth and development in these particular sectors, and in safeguarding the digital platforms, the information technology related applications of the country and of the world. So wish you all the best. My thanks goes to Dr. Giri and his entire team for taking up this effort in a relentless manner. Thank you all. Dr. Giri, now you can start the process proceeding.
Hello. Thank you for the audience.
I think Dr. Giri, there are some problems with your network.
Yes,
so my request
yes.
is now, Prem Kumar, you kindly see who
Yes,
among those persons, expert members who are going to deliver at the very beginning, and kindly, if you have data, kindly introduce him and request him to make his presentation or deliberation.
Yes, sir. So I'm checking whether Giri sir will be able to join very soon or not, and I'm continuing, sir. Giri. Hello, Giri sir.
Now I introduce Dr. Ashish Kundu, is a distinguished scientist, a leader in the area of security, privacy, compliance, and AI ethics, and distinguished speaker. He has recognized as an ACM distinguished member and earlier as a ACM distinguished speaker. Dr. Kundu has 150 patents filed and more than 110 patents granted and more than 40 research papers. He has lead security complaints to self-device cars, teleoperator device, UAV across.
Very interesting topic, blockchain and the Vedas connection. Very interesting.
Now he will speak. Now
Giri sir, I think you have some internet connectivity problem.
Internet
So
issue,
let
Giri.
Ashish
Yeah, yeah.
Kundu sir begin.
My
Yes, sir.
request, my request is
okay.
Dr. Ashish Kundu is kindly give a small self-introduction, because Dr. Giri is having all the details, but there is some connectivity problem with him. For the benefit of our participants, kindly give a small your self-introductions and start your this fascinating topic, blockchain and the Vedas connection.
Thank you. Thank you, Professor Maitra and Dr. Giri, for kindly inviting me to this webinar series. And it's my pleasure and honor to be able to present here about some of the findings about the blockchain and the Vedas connection. It has been a while I have been living in the US, but prior to that I've been born and brought up and studied in India for my undergraduate at NIT Rourkela and then master's at IIT Bombay. Then went on to do my PhD at Purdue University in Cybersecurity and Computer Science. After that, I was at IBM TJ Watson Research Center since 2011 till 2019 as a research staff member, and I also became a master inventor there. After that, I went on to head cybersecurity of self-driving cars at Neuro briefly, and then I went on to start my own startup, Session-VII, since beginning of this year. At Session-VII, we are focusing on some of the security and AI issues, particularly focusing currently the Indian market, and we'll move into the international market soon. My work is primarily focused around the notion called holistic security. Holistic security means that we want to find out the weakest link in the security path of security of that an attack path that an attacker tries to exploit, right? And unless we look at security in a holistic manner, in a 360-degree or an end-to-end manner, right, we will be just solving bits and pieces of the problem of security. We will not be hardening or strengthening security of a system. So in order to strengthen security of a system, it's essential that we look at all the aspects, starting with hardware to software to applications to programming languages to data to users to identity management to social engineering and everything else, right? So my work spans across all these areas, and I hear that my advisor, Dr. Elisa Battino, will be talking, I think, next week on 26th, and I'd love to come back and hear her thoughts that time. But anyway, I'll not take more time. I hope everybody can hear me. If you cannot, just please raise a hand. I hope in Zoom you can raise a hand, or you can actually send a message. So I'll try to do that. I'm actually sharing my screen over network, and I am calling using my US number. Currently, I'm in India visiting, but I will be back. But that's why I'm calling from my US number to Zoom number, and then I hope everything will go all right in this talk. All right. So I hope I didn't bore you enough here. The talk is blockchain and the Vedas connection, right? Essentially, this talk will look at two different categories of work. One is blockchain, which is the enabler for decentralized computing. Okay, the notion of decentralized trust, based on which Bitcoin and other cryptocurrencies work, right? And the Vedas the Vedas is the perhaps the most ancient literature on earth, and it has a lot of details with it. We'll come back to that later. But what we found briefly, just one sentence, that there is a similarity between the blockchain and the Vedas, the way they protect the integrity of the data. Okay, and that similarity is what we are talking as the Vedas connection. Okay, to also mention the Vedas being the oldest ancient, most ancient literature. Most ancient literature of the earth. It is also a religious text of the Hindus, but you can know that there is a notion of Vedic mathematics and other things. So we will not go into that aspect, the religious aspect here. We will primarily look at the Vedas as the literature or the ancient literature, and how its integrity has been protected across thousands of years, and what is its connection with the blockchain. But we'll spend good amount of time talking about trust, notions of trust, notions of decentralized trust. We will also talk about decentralized computing and then we'll go into blockchain, a bit of Bitcoin there. We'll discuss some of the blockchain platforms if time permits, and then we'll go into the Vedas connection. Right? I hope we have about 45 minutes. I'm going to spend about 10 minutes on trust, 10 minutes on decentralized computing, and another 10 to 15 minutes on the Vedas connection. Right? And we can leave remaining time for the Q&A. But if there are other things, please let me know, and then I'll wrap up some of the slides faster. All right. So let's talk about trust. Right? What is trust? Trust is essential when we define the notion of security. Right? It's essentially what we trust, what we do not trust. What we trust, what we do not trust, who we trust, who we do not trust, etc. So in order to start talking about trust, there cannot be a better statement than this one. That Ken Thompson, during our lecture in 1983, talked about a notion called trusting trust. It's a whole paper. You should look at that if you get time. Maybe you might have already looked at it. What it says here is that how much you can trust a statement in a given program. A program is a software program, or a firmware, or a hardware implementation of an algorithm, or it's not an algorithm, a heuristic, okay? Or maybe a machine learning algorithm. To what extent should one trust a statement that a program is free of Trojan horses, right? And when you want to trust, right, you look at a program, right? You write a hello world program, right? Now, in that process, you are going to suppose you wrote that program by yourself using C, okay? And C is where you are not making any library calls or anything. You can think so. There are no application libraries like in Java and Python they are. But in C there are standard libraries like stdio.h, etc. Right? Would you trust those libraries? Would you trust printf in C? If you look at Python, would you trust the printing statement? Just as an example, right? Now, would you trust that hello world program is free of Trojan horses? Trojan horses are what are the ones where the given program looks like it is benign, but there are malicious statements in it within the libraries or within the hardware implementation or software implementation or not within the obfuscated code that could be out there in that program, right? So that's why he says given the context of undecidability, given the context of the halting problem, right? It might be aware of the halting problem, right? It is hard to analyze a given program to see whether a program has security vulnerabilities or has Trojan horses or not. Right? I'm just making, there are other reasons for that as well. So that's why he says that perhaps it is more important to trust the people who wrote the software. Okay, that's interesting, right? It is at the end we are going back to source, the origin of the software, because we may not be able to trust the software itself. We may not be able to trust the statements themselves. If we trust the people, perhaps we can trust the software. Okay, so he's putting with a term perhaps that we should perhaps trust the software development team more than the software itself. Okay, and that's quite powerful, right? If you disagree with that, please let me know. And there are papers around this, and the trusting trust is more about, would you trust a program that is compiled by a compiler, right? A binary code also, right? Maybe the compiler has injected Trojan horses into the program, right? You can say, oh, my GCC works fine, lovely, it works smooth, right? But the GCC could be buggy. You might have downloaded the GCC from a mirror which has been compromised and which has been injected with malware in GCC, okay? Or perhaps you are going to run it on a cloud hardware or a host or a laptop that is compromised already. You must be knowing about Stuxnet and all the other glorious hacks already, right? So the whole notion of trust looks simple, right? But it's complex to establish the degree of trust, right? And that is why I'm spending so much of time on this statement. It was written and it was talked about in 1983, right? But it has been 37 years, right? And it will continue. This discussion is going to continue longer, right? And this is where comes the basis of blockchain, right? And this is where comes the basis of computing. As we go forward, we talk about trusted AI, right? Why do we want to trust AI? Right? Can we not trust AI as it is? Right? No, because AI is dependent on not only computing. Here we talked about the software. I have another talk where we essentially take the liberty to take this forward, talk about AI. Can you trust AI? You need to trust the data there. That is highly important, right? You need to be able to trust the models that have been trained. All those things come into. We will not focus on that. All right, moving on. So given that notion of trust, right? Given that notion of let's try to do a thought experiment here, right? We have Alice and Bob. They're two central characters and beautiful characters in cryptography and in security world, right? Alice wants to talk to Bob and Bob wants to talk to Alice. Or they want to carry out a transaction among them, maybe a Bitcoin transaction, right? But does Alice trust Bob? How would you ascertain that? See, it is one directional here. Does Alice trust Bob? Bob may not be trusting Alice, right? It's like, you might trust Google.com, but Google.com may not be trusting you. You might have created an account with fake names and fake information there. Therefore, Google.com may not trust you, right? But you will be trusting Google for giving the right search results, right? Similarly, does Bob trust Alice? The other way around, right? Do you trust Google.com? If you are Bob, right, do you trust? I'm not taking the gender inequality out here. I'm just saying that let's say these are two characters, which so let's not carry out to the we can interchange Alice and Bob, who is you and who is not, right? Or who is I and who is Google.com, right? So excuse me on that. I'm just giving an example here. That would Bob that is you trust Alice, which is google.com. Many times not. There is a plethora of work on privacy preserving search on Google. That Google learns a lot from what you search, right? And all your search results actually give out a lot of information about what you have been searching earlier or who you are. Right? Next question is, do they trust each other? Do you trust each other? Right? So Alice is giving a Bitcoin to Bob. Bob is taking that Bitcoin. Now, would you trust Alice? Maybe Bob is a ransomware creator who is or a propagator, who is taking the Bitcoin to take off the ransom or ransomware from Alice's computer, right? Or maybe Bob is a terrorist, okay? Or maybe Bob is a nice person who is Alice's friend, and they trust each other, and Alice is giving a Bitcoin to Bob, right? So these are the three different questions they ask each other, right? Now, the elements of trust, when we go into who trusts who, right? Who means the identity, right? Trust depends on the identity of the party, that is Alice and Bob. Right? Who is Alice and who is Bob? That question is something that you have to now when you define this, that Alice trusts Bob means who is Alice and who is Bob. If Alice is a different person than what we define as the identity of Alice, for us, Alice Prime does not trust Bob. Right? Similarly, Bob may not trust Alice Prime. Then what is the context of transaction? So trust depends on two elements, identity of the parties and the context of transactions. That's what we derived right now. However, before we go on to the notion of relative identity with trust, right? We want to talk about a brief, we'll digress into a notion called absolute identity, in philosophy, right? And because we are all as researchers, we digress into philosophy once in a while, right? So we'll talk about this one briefly for a second. It's called Aham Brahmasmi, which is primarily in India or in Sanskrit. Aham means I, Brahmasmi means the absolute. So I am the absolute. Here there are no notions of the relative identities, okay? So when you are I am the absolute, there is no notion of doing a transaction between I and I, right? Or defining my own identity. I have already defined that, right? So we'll not go into that. There is non-transactional in nature. We'll not go into that, right? So people who want to talk about it, that's a philosophical discussion, okay? So you might be asking, why am I going into this digression here as a slide? I could have removed that slide, but as a researcher, my job is to actually explore different aspects of identity and put it forward in the paper or in the notion. So it is self-complete to whatever extent I think of, right? We don't want to leave any citations or anything that we can, and that is important for the integrity of the completeness of the work of the researcher. So I'm trying to do that here. Okay. So we have taken off absolute identity of the table. Now we're left with relative identity, as we talked. So since identity is relative and trust is dependent on the identity, therefore trust is relative. Okay, the notion of trust is relative between Alice and Bob, between two persons, two programs, two hardware devices, two computers, two iPhones. Two. Now you can take two to any number, right? So, and that becomes the notion called trust calculus. Okay, so that is an upcoming paper, and the notion called the trust calculus. Okay, but that explores the notion of called trust is relative, right? Because identity is relative, and the context of transactions is also relative. Right? Now, let's pause here and understand what we have covered here. We have talked about Ken Thompson's notion of trusting trust, and how we should focus on trusting people more than the development team than software. Okay, for us that is more important. For us that is not. But the notion of trust is dependent on the notion of identity and context of transactions. And identity and context of transactions are relative in nature, and therefore trust is relative. Okay. With that statement, we want to move on to the next subtopic. Is called centralized computing, or there are different types of computing. Okay, and we'll then combine the notion of relative trust with the different types of computing. Okay, I'm going to pause about trust for now. Okay, we'll come back to that. So we have been since the beginning of computing, since the development of Enigma, okay, by Turing, and since the since we developed the mainframe computers at IBM, and till the quantum computers and everything, right? There is a notion called centralized computing. That computing is carried out at one system or maybe multiple systems, but it is a centralized notion that is the admin of the system, right? So many times people say centralized means the computing is carried out on one centralized system. Okay, this is what we are showing here. There's a logical diagram. Okay, but centralized essentially means, from a security point of view, who controls those computing resources, right? If it is a one centralized authority, then it is centralized. If it is multiple authorities, if the system is controlled by multiple authorities, then it can be centralized also. If those multiple authorities belong to the same authority, like a government of India or US government, there are different authorities. Right? Let's talk about the Department of Homeland Security and Department of Defense, right? Or Department of Education. They are different authorities, but there are certain systems they might control together, right? And we can perhaps say that they're centralized. In some context, we will not say they're centralized. Okay, we'll come back and say that is not centralized. That is what trust comes in. So take one centralized example of one centralized computing system where there is one VM, the top one. The bottom one, there is a VM, or there is a system, and there is a database. Right? There are two systems, two components there, right? And perhaps there is a cloud around it, right? So centralized computing can be talked about like a two-tier architecture where there is a client and there is a database, and a three-tier architecture there is a client, there is an application server, and there is a database. So you can actually take it to multi-tier architecture, right? In the interest of time, I'm not going to spend more time in this. So this is an example of centralized computing where a browser, you talk google.com, it goes to the IP services front end, the web server, then you go to application server, then you go to database server, right? Now the question of trust in the centralized computing, that can you trust the admin privileged users or roots of the centralized system? Let me go back here, right? This one. Would you trust the root of this VM, right? Or would you trust the provider of the cloud? So there is a lot of work on cloud security today. People say cloud security is important for hosting sensitive data, like healthcare data, right? Especially in US and European countries, right? Data security is extremely important. And also in India, they are coming up with the data privacy law, data security framework, etc. slowly. So if you want to host the sensitive data in a cloud, let's say AWS, right, or IBM cloud, right? Would you trust, because the owner of the underlying hardware and memory and the VMs or the hypervisor is actually Amazon AWS, right? They have an access via the hypervisor, right, to the memory of the VM. That is why the question is, do you trust the centralized services? If you trust the cloud, if you trust the VMs, if you trust the hypervisors and the databases, then you don't mind storing the sensitive data there, and that is where you need to talk about private cloud or hybrid cloud or multi-cloud architecture, right? Do you now imagine that the admin, maybe the cloud admin, or maybe the admin of the VM, or maybe the admin of the application, modifies the application code, right? As a client, right? As an external entity who is using the system, it definitely affects you in some way, perhaps. If it affects you, do you have any control on that? No, right? Does anyone else know that this code has been modified? No, right? So that in centralized system, trust, either you trust the centralized authority or the admins, or you don't trust them, okay? If you don't trust them, then you cannot trust the system, right? So the admin or the people who manage, they're going with a trust statement, right? If you don't trust the admins or don't trust those, don't trust the roots there, right? Or maybe the AI-based system which manages the system, then you cannot trust the output of that system, right? You cannot trust the data that is hosted by that system for you. Similarly, would you trust the database? So suppose there are database records of students with GPAs, right? There are faculties and students here, right? And suppose the admin loves or admin has an interest in changing the GPA of a student. That admin goes, modifies the database record of the student to 3.5 to 3.9 or 4.0, right? Nobody knows that unless the professor or the faculty admin or dean goes and sees there are some changes, right? So the student gets an advantage over the other person, right? So you cannot trust the admin there. So you cannot trust the system there, right? That is why, because you cannot trust the admin, privileged users, or roots of centralized systems, that is why there has been a notion called distributed trust. But distributed trust is not fully decentralized, means it is not divided across multiple authorities. It is the concept of decentralized trust which is democratizing computing. Okay, that is why we need to decentralize trust in systems where we are hosting sensitive data, we are hosting sensitive workloads, and which is going to affect several sets of people. Okay, or even if it affects one person, right? We need to ensure that the trust is upheld, and decentralized trust is essentially trying to do that. Is it a perfect solution? No. No solution is perfect, right? No solution is foolproof. No system gives you bulletproof security, right? That's like staff from Purdue University says there is no system that could give you foolproof security, right? So therefore, there's no notion of centralized trust that can achieve the kind of security we need in today's world, right? So therefore, it is decentralized trust which is important for us to understand, and that connects us to blockchain. So now at this slide, we can recollect what we have talked about. We talked about trust earlier. Now we talked about centralized computing, and we found the pitfalls of centralized computing with respect to security and trust. And therefore, it is essential that we need to have the notion of decentralized trust, right? And we'll come back to show that the notion of decentralized trust was not invented today. It has been invented from the time of the Vedas, right? That is the primary connection. Okay, so come back to that. Stay with me. All right. Any questions, or would you like to have questions later on, Dr. Giri?
Yes, sir. So the question will be taking the question answer session. Sir, please continue, sir. All the questions will be created at the question answer section.
All right. Thank you. All right. So I like this session to be interactive, but that's fine, For the webinar, I think it makes more sense to continue like that, All right. So by the way, I'm waiting for the day when we go into the virtual meeting room with the, and then have the kind of interactive sessions. And while walking down the aisle, we talk, right? So that would be beautiful then. But anyway, till then, let's follow this order of sequence, right? Thank you. So we have covered till now notion of trust, the notion of relative identity, relative transactions, and the notion of trust to be relative. Then we talked about centralized computing and why you need the democratization of computing, and that is enabled by decentralized trust. Okay, and decentralized trust is the concept that is based on blockchain and Bitcoin. Okay, now before I delve into blockchain, right? I should have the other slide here. Sorry for that. The slide on Bitcoin would have talked about that. Bitcoin was primarily started off in the paper came in 2008 by Satoshi Nakamoto, right? And we still don't know exactly what the identity of is, and but we trust the paper. In this context, we trust the paper, therefore we trust the individual. Is it one individual or multiple individuals? We don't know, right? Or is that a Bitcoin, or is that a blockchain of super intelligent systems who wrote that paper, right? It could be that, right? Who knows that, right? So, but I hope that it is some individual or one individual or multiple individuals, right? So Bitcoin is an application on top of blockchain. Right? Bitcoin offers a unit of coin. Okay, before we make it glamorous, right? It offers a notion of a unit of a coin, an economic unit that will be provided to each computer that solves a problem that is hard and can only solve can be solved only a computer who knows how to solve it, right? It's not a hash that somebody provides a hash, it's a hash that satisfies a certain type of pattern, right? So that was one type of Bitcoin, one type of cryptocurrency. I actually don't like the notion called cryptocurrency, because cryptocurrency is one type of such currency that can be developed on top of it, right? It is because of the cryptographic hardness of the mathematical hardness of the problems in the context of cryptography, right? But you can develop Bitcoin which are based on other hard problems, okay, that is out there, right? Or you can provide coins to computers as workers to do valuable work. The notion of valuable work, how do you define that? Here in Bitcoin is about mining a hash, right? But that's not that useful. Like you spend a huge amount of power, electricity, to actually find a Bitcoin, which is about $10,000 or $20,000, right? And that people say that's wasteful. But for technology, it is important to progress that area, right? Now because Bitcoin uses this finding who the workers are, you need to have a notion of democratization, right? You cannot say that a mine economic system doesn't incorporate people's input, how people use the money, how people work, and how people come up with the money. In this context, how computers work and how hard they work, and how much Bitcoins they can mine. So all these aspects depend on that these entities, each of these workers in a Bitcoin system or Bitcoin network, do not trust, because they work with each other. They work for themselves to mine the Bitcoin, okay? But they trust, they have to work with each other to build a notion of consensus, okay? That if somebody mined a legitimate hash with respect to the requirements of the legitimate requirements of the Bitcoin definition, right, or implementation, they have to agree with that. So that's how everybody will say, or a majority would say, that it is a legitimate hash. Now, that decentralized trust is essential, because if it is a centralized trust, then if somebody goes and they don't like their person, right, or they have something against their person, even if it is a legitimate hash, they'll say, oh, this is not a legitimate hash, right? So therefore, in the democratized computing, in the decentralized trust scenario, you need to have that everybody will act independent of others and validate or compute those rules using something called a smart contract. Okay. So a blockchain, essentially the underlying platform of Bitcoin, support the following notions, right? A peer, which is an independent worker, right? But takes participation with other peers in making decisions, not taking a consensus. There is a concept of consensus management, right? And there are consensus protocols, perhaps based on distributed algorithms or majority voting or whatever it is, right? Then there's the concept of a smart contract, which talks about the different types of rules that will define the notion of consensus management, right? And then there is an important part called ledger. A ledger is a database where records are appended. All the records, all the transaction records are appended. If all the parties or a majority of the parties, or there's a consensus about a record, they append that record and move forward the pointer to the next record. Okay, so it's a hash chain, and that's why it's called a blockchain, right? So it uses a hash chain. You hash the first one, then you add the next block, hash that, add that to hash chain, then you take the next hash forward, right? So, and these hashes are not your hash table hashes. It is cryptographic hashes like SHA-1, SHA-253 or whatever, right? Sorry, SHA-2, etc. Right? My bad. So, and they sometimes use Markov hash techniques, and there are different hashing techniques that are out there, right? So essentially, the key elements are the decentralized peers that are there. They work independently of each other. That's why they are untrusted. In a way, you can say they are semi-trusted because they trust each other for the consensus management, right? There is a consensus protocol. There are smart contracts, and there's an immutable ledger that can only be appended to. Okay, and the ledger is replicated, fully replicated across all the peers in Bitcoin. Okay, but if you take Hyperledger, right, you don't have not all the peers have access to all the ledger entries for privacy reasons. Okay, all right. So there are different blockchain platforms called Hyperledger Fabric, Ethereum, Hydrochain, Ripple, Core, and there are many of them. There are about 1,500 different crypto coins right now, right? And that it's interesting. It's like mushroom effect, right? So maybe they are reusing many of them. Maybe they are reusing Ethereum or Ripple. Okay. Some of them are Core, but maybe they are developing some of them anyway. Right? All right, we will not spend much time there, right? For the interest of time, I'm not going to get into how Bitcoin works. So Bitcoin, similarly, but I'll provide a brief topic as I mentioned earlier. This is what I talked about already. I'm going to move forward here. Okay, the consensus protocol is proof of work, and there are many other consensus protocols like PBXT protocols. There are there are many other different consensus protocols that are being developed. Okay, but the question is, can you actually break consensus protocols? And if you break consensus protocols, you actually take over the blockchain network in a way, right? And interestingly, when I was at IBM Watson Research Center, me and some other colleagues were having lunch or coffee. I don't remember exactly. I mean, the cafeteria we were chatting about this problem, and I mentioned that there will be a point when there will be taking over of this the consensus protocol, especially on Bitcoin. When you have more than 50%, like the majority is there, then the Bitcoins are going to be who owns that 50% of the peers, right? And that has happened. You look at the work at some point that has happened for us. People talk about there's a country who owns some of the who owns more than 50% of the peers at some point, right? I'm not going to name anyone out there. Okay, don't get into any political mess, right? Okay. But anyway, and that is why the blockchain system is not also foolproof, because you can break consensus. Now, if you can break SHA-1 or SHA-2, you can the hashing technique used in Bitcoin, you have broken it. You will become a billionaire in no time, right? Maybe you can spend time on breaking the hashing technique used in Bitcoin, right? But it is not easy. Okay, it's hard. All right. So given that, I'll get into the notion of the Vedas connection. So Dr. Giri, how much time do I have? Because I don't want to delay the other speaker.
Sir, you can take some time, sir. It is open. So you can complete your talk. Sir, it is around 40 minutes you can take, sir.
It's a very beginner level. So there is a possibility that many of participants.
Sorry, I couldn't hear you properly. 30 minutes, did you say?
Yes. Yes, sir. You can continue the talk, sir. You can continue the talk. We have time. We have time, sir.
All right. I cannot hear you. My apologies. Maybe if you can send me a chat message, maybe that could help. You know. But okay, I'm going to take about 15 minutes or more than that. If you give me more time, then that'll be okay. But about 10-15 minutes on that. So, okay, thank you. I don't see the message here. All right. Okay. So the Vedas, right? Let's pause here about decentralized computing, about Bitcoin and everything. You know, let's clear our stack. Let's create another memory stack for our own benefit, and we'll come back and pop that stack, and I'll get back to blockchain later. Okay. We'll start off the other part of the talk is the other Vedas. How the integrity of the Vedas was maintained. You know, let's ask that question. Well, first of all, what are the Vedas? By the way, this work, the Vedas connection with blockchain, is a joint work with my ex-colleague at IBM Research, Arun Ayachitula, and Nagamani Sisla. Okay, Nagamani Sisla is a friend of mine. He's Arun's wife. So the story goes like this: that I was thinking about thinking of blockchain and what the other things. Is blockchain original or something? We were discussing about that. And Arun and Nagamani, called as Mani, I was having a coffee at their place at one evening, and then in 2018, and then we talked about the Vedas. They know the Vedas to a good extent, you know, and they talked about the notion called pathas and how the pathas are patterns in the Vedas, how they are used to verify the integrity of the slokas of the Vedas, and that led to this discussion about perhaps there's a connection of the Vedas integrity model with the integrity model of the blockchain. Okay, and that is where it started off. So I wanted to credit my collaborators here. Okay. So the Vedas is an Indian ancient literature. Okay, we don't know who is the origin of that. We don't know who is the author of that. Okay, it is a collaborative work. There is no centralized authority. And interesting. So it's basically decentralized. There are let's say there are independent authors or whatever, right? We don't know who they are. And it is disseminated as Shruti. Okay. Sorry for the it should be SHURUTI. Okay. It is primarily disseminated as Shruti, not Smriti. You know. So Shruti means from generation to generation, from one person to the other, that disseminate the Vedas by recitation, okay, by chanting, okay, or by recitation, okay, and people hear that and then remember that, okay, and then they propagate or they give out the Vedas to the next generation similarly. Okay, and that's the primary reason for that. People could say, why was not written? Because one of the reasons is because at that time maybe there was no way to propagate the writing. It was in a language that we understand now called Sanskrit, but there is no way to write it that will remain preserved for tens of thousands of years. That is one reason. The other reason is the sound. The sound aspect of the Vedas is so important that just by writing it down, you will not preserve how the Vedas slokas are chanted or how they are uttered or pronounced, right? Okay, so we leave it there. And there are also new shlokas or padas that are added from time to time. To time means the time is very like 100 years or 200 years. Okay. So the Vedas have 4 Sangitas, or 4 different parts. There are 89,000 padas. Padas means the stanzas. Okay, and it is for the oldest ancient literature. There are some citations there we see, and also Scarf from Germany. He has written a book called Memorizing the Vedas. Okay, so look at that. There has been a number of non-Indian authors, like Western authors, who have looked into the Vedas and written a lot of books. And I'll encourage you guys to look at both Indian and non-Indian authors. So given that there is no central authority, it is transmitted or propagated using Shruti as a Shruti, right? It is easy to compromise the terms and shlokas. It is easy to compromise the pronunciation. It is easy to compromise the semantics, right? Because there is a central authority who can say, hey, this is incorrect, right? So it's important then for the meaning, the semantics, and because it is a religious text, you need to preserve its integrity fully. But because there are scientific angles to the Vedas, on the science of sound, on mathematics, right? You need to preserve the correctness and integrity of the syntax, the semantics, and the phonetics, right? And the stanzas, of course, right? And also you should allow collaborative updates. Isn't it similar? From these goals, you look at the goals of the blockchain or the bits, right? You want to preserve the correctness or integrity of the rules, right? You want to ensure that the integrity of the ledger is there, because otherwise somebody will modify it to say that an invalid Bitcoin is a valid one, right? Or somebody can modify a ledger saying that, hey, one record was invalid, but it is now valid now, right? And there could be collaborative updates, right? So there's a lot of similarities. We'll come back to the similarities in a bit. Right? So given this integrity threat to the Vedas, right, how do you ensure that the Vedas have remained uncompromised till now? And there has been some work, okay? There has been work on that. There is no textual corruption on the Vedas. How do you manage that, given the scenario? Right? And this has been for thousands of years. The way they manage it is about having few components, right? One is about they use a notion called patha, and patha is a term that is used to describe the patterns. There are 8 different types of patterns used, right? So patterns is like encoding, okay? You take a given stanza, okay, or a textual representation of one stanza, and then you encode it. You place different terms one after another, and you encode it in a way with respect to the rules of that pattern. Now, there are 8 different patterns, and those 8 different patterns are called jata, mala, shikha, rekha, dhwaja, danda, ratha, and ghana. Right? These 8 different patterns are used to encode the weather. So that means that there are 8 different types of Shrutis or 8 different encoded versions of the weather. Right? And there is one group of society per pattern. So the society was had one group, okay, which was developed to preserve one pattern, one patha. So they would be responsible to actually propagate the weathers in that pattern as Shruti. They'll take the weathers in that pattern from one generation to the other, right? So basically Ghanapathis, right? Ghanapathis are the ones that take, they recite the weathers encoded in the Ghana pattern, okay, or Ghanapatha, okay, and then they'll recite and the other generation, other persons, they will remember it and take it forward, right? If there is an erroneous addition or attack on that pattern, that is the group which will identify that and prevent that, right? Now there is periodic consensus that helps identify compromises. Suppose there is one attack that actually compromises the pattern, but is not detected, determined, or identified by that group, right? Like Ganapathis cannot determine a compromise of Ganapatha of the weathers and an erroneous addition or compromise of the weathers, right? Suppose that happens, right? The probability is low. But if that happens, right? It is not as low as like modifying a hashing technique, because it's a mathematical encoding. It's not as hard as the mathematical problem of hashing, right? So perhaps that's why there are 7 different other patterns which will determine that there is an erroneous attack, there is an attack or there is a compromise, right? So therefore, you need a periodic consensus among all these different groups of society, all these 8 groups of societies, to actually come together at some point, like periodically, okay, and say that, hey, I find that there are some compromises there. Okay, so you have to go back. So you have to actually replicate your ledger. You have to ensure that your ledger is correct. Okay, so you look at our ledger which is correct and then replicate it into your pattern, right? Similarly, that's all. And also they can help by consensus add new steps or add new stanzas, okay, in their pattern. So that is a summary of how the integrity model of the weather, right? To give an example, okay, the Ghana pattern, right? The bottom lower one, sorry, the right hand side lower bottom, right? This is the one, right? Sorry. Okay, now I'm trying to get back to my presentation here. Okay, here. All right. So you look at the stanza has 1, 2, 3, 4, 5 as the terms, right? The Ghana recital will be like this following, right? It's the first 2 terms will be together, 1, 2, like 1, 2 in the sense there might be a space, there may not be a space, okay, but there will be a space. So 1, 2, 2, 1. So 1 will if it is 1, 2, 3, 4, 5, then there will be 1, then 2, then 2, then 1, then 1, 2, 3, 3 to 1, 1, 2, 3. Okay, it's like they're creating a palindrome kind of thing, right? Then 2, 3, 3, 2, 2, 3, 4, 4, 3, 2, 2, 3, 4, something of that sort. Then at the end is 5 with the 5, right? So if suppose you want to add a new term called 6 after 5, right? So you can identify. So then this pattern, they cannot just insert 6 EP6. No, they have to insert 6 EP6 1. They have to insert it in almost half of the places, right?
Hello, Ashish sir. Hello, Ashish sir.
Hello.
Yes.
Ashish sir, your PPT is not visible, sir.
Hello. Yeah, I cannot hear you. Do you want me to complete? Finish the talk?
Sir, I have posted that there your PPT is not. Sir, kindly
Okay,
check
yeah, I'll be
the.
done in I have. Hello.
Sir, please check the post message, sir. Yes.
Dr. Ashish, your PPT is not visible. Yeah, now it is okay. Now it is okay.
Okay. All right. Okay. Thank you. Yeah. Sorry for that. Don't know why. Okay. I'm going to spend next 5 minutes or 10 minutes like this. Okay. I've only 2 more slides or 1 more slide, right? So let me try presenting once more. It's not. It's taking time. That's fine. Okay. Let's stay with that. Okay, I think I'm having a network connectivity issue here. Let's see what is going on. Can you hear me? Hello? Can you hear me?
Yes. But your slide is not visible.
All right. Okay, so I'm going to present it here. Give me a second. Okay. All right. I hope it is visible now. So we talked about till now we've talked about the integrity model of the weathers, that they have 8 different types of patterns in which they encode the weathers, stanzas or shlokas. And for each pattern there is one group of society which preserves that pattern, that is for thousands of years. And there is a periodic consensus among those 8 different societies, group of societies and maybe others, to have a periodic consensus. Okay. And and then also to allow to determine compromises to the Vedas, also to add new stanzas or shlokas. There is an authoritative figure on the Vedas who has come up with those shlokas, okay, or stanzas. So just talking about the Ghana recital, and we can go into the other recitals, the Rekha recital, which is on the screen as well. But I'll not go into that in the interest of time. In this context, the Ghana recital, if you want to modify Ghana recital by adding one term to the end of the term or to in the middle, right? That is going to that means that we have to add that term not just one place, like in the original order of words, but we have to add it at about more than 50% of the places. Like if you want to add something after 3, that's a 4 prime, right? 4 prime will be added at about 11 places here. And how many stanzas, how many encodings are there? About 19. So 11 out of 19, basically more than 50%, 60% places you have to modify. Okay, so that's that is a problem there, right? And it has to also ensure that because of Shruti, because of the hearing, that the pronunciation should be okay, the semantics should be okay. So all those things are looked at. Okay. Now, what are the similarities here? The human blockchain of the Vedas and today's digital blockchain, right? Remember, in the human blockchain of the Vedas, it is a human group of society who act as peers, right? So integrity is supported as in the patterns called as charter. So left side is for the Vedas, right side is the digital blockchain. So integrity is supported by patterns called as charter. Those are the encodings, right? Then that is similar to the hashing and error correcting codes that we have, especially hashing that is used in blockchain. 8 different types of patterns. There are 8 different types of patterns in the Vedas, right? So for its integrity checking. In the Vedas, there is only there is one hashing scheme that is primarily used for the ledger, right? But this is a learning from the integrity model of the Vedas that for stronger security of the Vedas, we should use multiple hashing schemes. So suppose in one hashing scheme, as I was mentioning, is broken, then the other hashing schemes will provide protection of the ledger. One group of society preserves one pattern, right? Similarly, here there are peers and minors. So one group of society in the Vedas is similar to the peers and minors in today's digital blockchain, right? And they can be in the Vedas, we can call them as peers as well, right? And periodic consensus helps identify compromises in the Vedas. In the case of the digital blockchain, it is the consensus is the ledger, right? The ledger essentially in the blockchain is the ledger, right? The hash chain of the records and the hash chain, right? And is immutable. It protects the lineage and provenance, and there is a consensus on it. In the Vedas, similarly, they have a consensus mechanism. They have a ledger. The ledger is essentially the way the Vedas move forward one step to the other. There is an open. There is immutability that is hard to modify because of, and if it is modified, then it should be allowed using the consensus mechanism. And it also preserves the lineage and provenance of the Vedas. So what we are essentially talking about here is that blockchain has ushered in the concept of decentralized computing and has enabled a lot of different types of transactions that could not be possible earlier, right? And that has also helped harden security of certain systems, provide better security models, right? But it doesn't mean that blockchain always enhances security, okay? So people will say blockchain enhances security. No, not that. You have to look at the context and understand where you are using blockchain, right? So the decentralized trust of the blockchain enhances trust in that way, in some ways, right? Blockchain also helped develop the whole notion of economic model called the virtual currency model, okay, the bitcoins and others. But even though it looks so original, there is a parallel that has been existing since thousands of years in protecting the integrity of one of the most ancient literature on earth, right? Then that is what we discovered, and we wanted to bring it to you. That there are similarities in the elements in the both technologies. Right? The technologies of the blockchain has the different elements there, the ledgers, the consensus management, the peers, the hashing schemes, the integrity model of the Vedas have the similar set of elements. And the ledgers in the Shruti, that is the way they record the states and the standards of Vedas. The peers, there's a consensus protocol there, management technique there, which we are, I'm not talking about here in detail here, and I'm not an expert in the Vedas, by the way, nor I know even too many things. I know only basic things here, okay, with respect to this context here, right? Only that much I know. But then there are peers and minors, like a group of society preserves some patterns, and there are hashing schemes like the encoding here, because they are not using mathematical hashing, they are using mathematical encoding, and there are 8 different types of encoding. And we learned that perhaps we should use multiple hashing schemes in the blockchain network at some point for better security. Okay? So that's the summary, that there is similarities, perhaps you can learn, or perhaps the learning should be bidirectional also. Okay? So, and perhaps there are other ancient literatures around the world from different societal groups, from different countries. Perhaps they also use similar technologies. I would encourage other researchers to actually go and find out those aspects as well. Okay, but I'll take that, as an Indian-born person, I take pride here that there is such similarity, and the concept of blockchain did exist, or the notion, the way blockchain works, that way did exist earlier, thousands of years earlier in the culture, and we have also contributed to Vedic mathematical work. Yeah. So with that, I'm concluding the talk here. Any questions and thoughts? You can also counter. You don't have to agree with me. Okay, as a researcher, this is a finding, and you feel free to disagree with me as well. Okay. Thank you.
Hello.
Hello. Sir, there is a one question in the question and answer section. Sir, please, sir.
Sorry, I cannot hear you. The network connection is not
Sir,
that great.
now can you hear me? Hello.
Yeah, a bit better.
So now, yes, sir. So the question is that, hello, yeah, Bitcoin uses UTXO and Ethereum uses a different method instead of
Hello.
UTXO. What is the method in Ethereum?
If someone who has a better internet connection, can someone read out the question to me, please?
Sir, you can see the question in the question answer section.
Okay, I'll stop sharing. Okay, I hear that there are 2 queries. Bitcoin uses UTXO and Ethereum uses a different method instead of UTXO. What is the account method in Ethereum? Right. So I haven't used Ethereum that much as I have used Hyperledger in IBM research. So I'm sorry, I don't remember of the hand the account method in Ethereum. Sorry for that. You can look up, but you can take it offline, okay? And if you have any problem in determining that, let me know. I'll find it out for you. But I used Hyperledger a lot being an ex-IBM. So the next question is are there 2 types of blocks in blockchain, normal blocks and miners? Not really. So you look at the blocks, right? The blocks essentially represent state of a blockchain. Okay, there's a notion called world state. Okay, and the world state represents the state across all the entire blockchain system, right? So a normal block essentially represents the transaction. Okay, now there could be, depends on how you have implemented the blockchain system, right? I could implement it different than the way Bitcoin uses its blockchain, right? I can have a block there that represents certain meta information about miner. You can have that, or it could have also forking. So Ethereum went for a forking sometime earlier because its primary ledger was compromised. Okay, and some ethers were stolen or something like that sort. Right? So we can have different types of blockchains, right? It need not be only one type or two types. Right? The next question is that I've read that if any new block generator solve the security puzzle or proof of work, and the new block will get another chance to solve it. When a transaction can be rejected in blockchain, okay, a transaction can be rejected in blockchain if it cannot be validated by the consensus protocol. Okay, so suppose you in Bitcoin, suppose you say that you solved the cryptographic puzzle and posted it as a transaction to the Bitcoin network, right? So the consensus protocol there, which is proof of work, will then validate it, okay, and when it is validated by the majority, right, then your block is added. If it is not validated by the proof of work protocol or the consensus protocol, right, then it will be rejected. Okay. Does that answer the question? Yeah. So
Thank you, sir, for the answer.
okay.
Giri, sir, are you there? Sir, I think you are
Any other questions?
able to hear. Can you hear us, sir? Ashish, sir, can you hear us?
Yes, I can hear you with some noise there. But yeah, please.
Yes, sir, yes, sir. I think there is some internet connectivity problem. So, sir, there is no more any questions, and the question has been answered. So we move forward. Giri, sir.
Yes. So and
Giri, sir, hello.
if there are questions, please send me an email at akundu@scm.org. Okay, that's my email address, and feel free to send your questions or what you liked. If you didn't like anything, or maybe scientific queries or anything, right? Likings or claims also, please share that. I'll be happy to respond to you if time permits, and your questions also. I'll be happy to answer them. Thank you, and thank you so much, Dr. Giri, for hosting me, and for the privilege and honor to present here on this topic of the blockchain and the Vedas connection. And thank you so much, Dr. Saikat Maitra as well, for your time. And thanks everyone for. I hope it was audible and it was clear. And sorry for any disruptions in between because of the share screen went away. Thank you so much.
Thank you, sir. Thank you very much. And sir, sir, sir. Hello. Giri, sir, hello.
Hello, yes.
Yes, sir. So, we are moving the next talk. That is from Dr. Kirill Morozov, sir. And Giri, sir, hello. Dr. Kirill, sir.
Hello?
Can you hear
Yes?
us?
Yes, I can hear you well.
Yes,
Yeah.
sir. Yes, sir. Yes, sir. Sir,
Sure.
due to some internet connectivity problem, Giri sir is not able to get connect. So let me introduce to the participants that Dr. Kirill Morozov sir is from University of North Texas, USA, and he will be delivering the next talk. So, sir, please give your valuable speech and continue with your presentation, sir. Giri sir, hello.
Hello,
Giri sir?
are you getting my voice? Hello,
Yes, sir, it is
Nandkumar, are you
breaking,
getting my
sir.
voice?
Yes, yes, now it is, sir. Continue, sir. Yes, yes, I was just giving the introduction for the Giril, sir. So please, sir, continue, sir. Sorry, sir, due to some network connectivity, Giri sir is not able to tell.
All right.
Kiril sir, so please continue, sir. We will have the introduction session at later on. Yes, sir.
Should I
So
continue?
please,
Okay.
sir, Kiril sir, sorry,
Right.
sir, and you will just give a small introduction from yourself, sir. And sir,
Yes.
please continue with your presentation, sir.
I will continue. Thanks.
Sorry for the technical delay, sir.
Not at all. No problem.
Yes, sir. Yes, please, sir, continue, sir.
Okay. Do you see the screen?
Yes, sir, it is visible, sir.
Yes. Okay. Great. All right. Good evening, ladies and gentlemen. It's morning here in Texas. First of all, I'd like to thank you for your kind invitation. It's a privilege and a pleasure for me to give a presentation at this webinar series. It's the first time for me to broadcast to a large audience and to do a webinar in India. So I'd like to tell you about code-based cryptography. I realize that some part of the audience may not be familiar very closely with concepts from cryptography, and that's my topic of research interest, cryptography and cybersecurity. So I will try to be somewhat informal, and I will try to give some high level explanation of the concepts that I will present. So let me go ahead. And first, I will give a short introduction about my institution, University of North Texas. Then I will give a brief introduction to code-based cryptography. I will discuss hard problems related to coding, and also give some basic, some classic results based on them. Then I will give a motivation why we should consider exactly this type of cryptographic functionalities. I will talk a little bit about post-quantum cryptography and the threat that quantum cryptanalysis may pose. And then I will continue with recent results in code-based cryptography. I'm not really following the time precisely. I assume I have about 1 hour for the talk, and otherwise, please interrupt me at any point about 10 minutes before my talk should finish, and I will wrap up quickly. So, University of North, yes?
Yes, sir. We will inform you, sir.
Okay, yeah.
Kirill,
So,
hello, are you getting my voice? Are you getting my voice, Kirill?
hello, we can
Hello?
hear. I can hear
You
you.
see,
Yes.
just let me introduce little bit
Thank
because you see
you.
I was disconnected. I am having a network problem. So just
Great,
little bit
great.
of introduction.
Thank you.
Okay, Dr. Kirill Morozov received his PhD degree from University of Aarhus in Denmark. He is currently as an associate professor in the Department of Computer Science and Engineering, University of North Texas, USA. He has about 20 years working experience in research and academic in Russia, Denmark, Japan, and United States. his research area is mainly focused on cryptography and cybersecurity, and in particularly design analysis of post-quantum cryptography protocol based on the coding. And now I request to Dr. Karel continue your speech.
Thank you so much. Thank you for
Because
your
I am
invitation.
I am having some network problem. That is why I was disconnected from
Yes.
many times. Okay, okay. Sorry for that.
Not at all. You're right on time with your introduction. Thank you so much. So,
Okay,
as
thank you.
Professor Giri just mentioned, I am now at the University of North Texas. So this is the university which is celebrating 130th anniversary this year. It is a tier 1 research university according to Carnegie classification. And just this year, so our enrollment is constantly growing. And just this year, we got 40,000 students enrolled. So the university is located in Denton, Texas. This is the part of the Dallas-Fort Worth Metroplex. It is close in Texas standard to DFW International Airport. So we are quite well connected in terms of international travel. Regarding cybersecurity research at UNT, we have a Center for Information and Cybersecurity, and also Network Security Lab, which are both directed by Professor Ramdantu. The lab has 3 faculty and 12 students, and our research interests cover the areas written here. In particular, these are blockchain applications and smart contracts, cryptography, denial of service, protection against denial of service attacks, security of video streaming and voice over IP, and monitoring, health monitoring using smartphones and smartwatches. Regarding cybersecurity education, just this year we introduced a master and bachelor degrees in cybersecurity. So we are one of the few dozens such programs in the United States. Also, through the efforts of our center, UNT has been designated as National Center for Academic Excellence by NSA and DHS, and this allows us to offer respective certification to the qualified students. So now I would like to switch to introduction of code-based cryptography. I'd like to tell you first that the history of code-based cryptography started in 1978, near the time when the public key cryptography appeared. So Robert McAleese introduced his seminal result, a public key crypto system based on algebraic coding theory in 1978, 1 year after famous RSA crypto system. I'm just giving here the excerpt from the abstract of his report. It was, so he mentioned that using the fact that a fast decoding algorithm exists for a general GOPA code, while no such exists for a general linear code, we construct a public key crypto system which appears to be quite secure, while at the same time allowing extremely rapid data rates. So all those statements hold today as well, and I will discuss those in details. So the idea was to build a crypto system which is based on hardness of decoding problem for certain type of codes. The motivation to work on this system is that it withstood over 40 years of cryptanalytic attempts by the research community worldwide. It is based on decades-old hard problem decoding random linear codes, and it is also a post-quantum candidate, meaning that it is believed to be resistant to quantum cryptanalysis. This system actually a basis for the classic MAKAUT submission, which is now the round 3 finalist for the US National Institute of Standard and Technology Post-Quantum Cryptography Standardization Project. So motivation for transitioning to post-quantum crypto system, why it is important at all. If we look at the information technologies which use cryptography as the underlying security mechanism, we could see that there are 3 major concerns there. One of them is constant growth of computational power. So we got more and more powerful computers, and we have to constantly evaluate security of the existing cryptographic systems and keep the key size up to date, which the community happened to succeed up until now. The key size is growing, and the systems are updated relative to the growing of the computational power of the potential adversary. Some of the issues may arise with the progress in cryptanalytic algorithms. Again, we may deprecate the system against which an attack can be mounted, and again the community was able to cope with this threat for decades. By now we have a set of cryptographic algorithms which has been standardized and implemented for security of the internet protocols. So when, for example, you access your internet banking, or you call on your mobile phone, or you use instant service messaging such as WhatsApp or Skype, then behind there is a there are cryptographic protocols which use those primitives. However, recently there was an issue of the so-called quantum attacks. The problem was that a new type of cryptanalysis has been introduced that based on the new concept in the computation, which is called which are called quantum computation. So the next generation of cryptographic algorithms, which must be used, for example, for protection of the internet transaction, must be post-quantum, which means they must withstand quantum cryptanalysis. If we look at the development, if we just look at some piece of timeline in development of quantum computation, we will notice that quantum computation has been developing very fast in the recent years. So this is the picture of a component of the quantum computer at UC Berkeley. So this is just a component which takes half a lab. Then in 2012, we had a solid state quantum processor. So this is basically a quantum device which has the size of the regular CPU, maybe a little bit bigger, but basically it has a size of a regular CPU in our computer. And it had it had 9 quantum elements. So basically it was able to run a 3-qubit version of Shor's algorithm. So now we have a cloud access to the 16-qubit processor, with the underlying SDK and the programming APIs for that and the community support. This is provided by IBM. On the behind, you will see basically artistic rendering of such the system, but you can actually you can actually sign up and you can have access to this quantum computer and you can run some quantum algorithms. And IBM is rumored to work on few dozen qubit quantum computer at the moment. So to give you a perspective, at the current state of the art, we will need thousands, possibly millions qubits processor in or a device to be able to break current cryptographic schemes. So we are only at the very beginning of this path. However, given the speed of the development in quantum computation, it is important to prepare the next generation of the cryptographic schemes to switch to. So how does the transition to post-quantum cryptography progresses? What we had since beginning of 80s until nowadays, we developed a set of cryptographic functionalities that was enough for satisfying basic needs for cryptographic protection. We have a good understanding of the security of those systems. We have implementation on various platforms, and we have those primitives standardized and used for internet security. In 94, Shor's algorithm has been introduced. This is a theoretical algorithm which allows to break RSA crypto system and Diffie-Hellman key exchange given a working large-scale quantum computer. So since early 2000s, early prototype quantum computers started to appear. And at some point when full-scale quantum computers will appear, we will need to switch to the new generation of cryptography, which we will call post-quantum. We have a number of candidates and they employ hard problems which come from coding, some algebraic tasks such as multivariate quadratic equations, lattices, and other mathematical objects. We have quite good understanding of the security. We have quite a few implementations again on different platforms, but what are missing are the standards. And this is critical for the industry. Industry needs standards in order to implement security mechanisms that we would use in our operating system and for protecting, for example, internet and banking transaction. So to respond to that, NIST post-quantum cryptography project has been launched. So in round one, there were about 60 submissions to be considered as post-quantum algorithms. Round two in 2019 left only 26 submissions. And now we are in the round three, where only 7 submissions are remaining, and they are considered finalists. So among those, 1 or 2 algorithms in each category will be probably chosen, probably next year, and then we will finally have post-quantum standards. So one of the systems which are the post-quantum candidates are code-based cryptographic systems. So one of my research interests is design, security evaluation, and implementation of such schemes. And I will tell you the story how such the crypto systems function and what is the intuition behind the security. For now, a little bit more of the intuition. So the question is transition or not transition to post-quantum security. That is the question, whether we should do it. So of course we have three options. One option is do not transition. However, that would be a risky choice, and I will explain next why. Probably in the midterm, what we will see is the so-called hybrid approach. It means that we will somehow combine the existing, what I call in quotes, pre-quantum scheme and the new post-quantum schemes, to make sure that if at least one of them fails, then the other of them will hold the fort. And eventually, in the future, we will move to completely post-quantum systems where pre-quantum schemes will be deprecated. So that probably will happen in the long term. The particular schedule is not known, and it depends on the progress in quantum computation, which, as I mentioned earlier, is at the early stage. However, since it may be difficult to project what will happen, for example, this decade, it may be risky to delay transition to post-quantum cryptography. The reason is because the key exchange mechanism, which work for the internet security, uh, if you heard HTTPS and transport layer security protocol, they use post-quantum crypto, which would be RSA, Diffie-Hellman key exchange, or its elliptic curve variant, and all of them will go if the full-scale quantum computer will implement quantum cryptanalysis. So the problem with the transition, why it should happen as soon as possible, at least to the hybrid primitives, is because communication that are secure today in the post-quantum present may be leaked later in the post-quantum future. The high-level picture of the internet transaction is as follows. Whenever, for example, I or you connect to my online banking via the browser, first the key exchange protocol is going to be run, a key for symmetric encryption is going to be established, and then this key is going to be used for confidentiality and data integrity to establish secure channel between me and the bank. So the good news is that careful choice of symmetric functionalities will provide security. So secure channel part is okay, even in the post-quantum world, again, with a careful choice of primitives and the parameters, which we can arrange. The problem is that in the upper part, the key exchange is based on pre-quantum primitives, and therefore it may be broken when the quantum computers appear. Now, the problem is that if the key exchange is broken, then the key will be learned, and therefore security will be gone for secure channel as well. Secure in quotes, because the key now will be known to the adversary. So it's enough for the adversary to record sessions that are sensitive, keep this recording for the future. When the quantum computers will appear, they will just break it, break the part 1 key exchange, and then they will just read part 2, which will be secure channel. So transition is recommended, at least to the level of deployment of hybrid primitives. And we have the following choice for the so-called asymmetric or public key cryptography. The list is not exhaustive, but it contains the main candidates. We have the cryptosystems and signatures based on coding, lattices, multivariate quadratic equations, and isogenies on elliptic curves. And also, if we want just signatures, we can deploy cryptographic hash functions or combination of symmetric ciphers and zero-knowledge proof systems, which I will not focus on in this talk. So here is a motivation to study code-based cryptosystems. It is based on decades-old hard problem, decoding random linear codes. Post-quantum candidate, it's resistant to quantum cryptanalysis. Actually, the candidate that I mentioned, classic MAKAUT, is a result of a merger with another submission. So as a matter of fact, you could consider that two submissions, two code-based submissions made it to the final, and also two code-based submissions are considered as an alternative candidate. So they are not officially finalists, but they are kept as an alternative candidate in case something will happen with the finalists. In other words, code-based cryptographic system represents a good pool of candidates for the post-quantum cryptography. And due to the fact that many of them work so easily compatible with binary operations, they are going to be fast in hardware and software, although certain challenges remain, and then I will mention them. Yes, is there any question? If there is a question, please feel to interrupt me. If you would like me to if you asked questions, because I may not be able
Sir,
to see
please
them.
continue, sir. Sir, there was a little bit
Okay.
noise from the.
Okay, I
Sir.
see. Yeah, if you cannot hear me well, please tell me. And I actually, I'd be okay with being interrupted. So if somebody asks me question in the middle, because I want you to
Yes, sir. Yes, sir.
understand as
It is
much as
open for. It is
possible.
open.
Yeah,
So
very well.
participants are requested to kindly,
Just
if you have any question, you can post it.
good.
Otherwise, you
Yeah.
can raise a hand and ask question.
Yes.
Okay,
So
sir. Sir,
the
please continue.
yeah,
Sir.
yes. The problem is that I may not see the question there because I am in the full screen mode. So if you guys from the support
Sir.
team just
Yes, sir. We will
interrupt
let you
me.
know, sir.
Yes,
We will
very
let
well.
you know, sir.
Thank you.
Yes,
Thank you.
sir. Thank you.
So that's for the motivation. So let me now talk about a little bit about linear codes and the related hard problems. So another kind of informal motivation why you may consider working on code-based crypto, it is connected to algebraic coding theory. Yes, there is a strong connection to algebra to that. And I know that there are lots of good algebraists in India. So I heard you guys are pretty strong on algebra, and therefore that's another motivation for you to look at code-based systems, because you will see lots of familiar concepts. Very well. So brief introduction to linear codes. Yes. Linear code, yeah, and I will not go into details about actually constructing or decoding linear codes. So just a very high level overview. So if we talk about linear code, a linear code is nothing but a linear k-dimensional subspace of binary vectors. So when I write F2, I really mean GF2. This is just a binary field. So F2, F subscript 2 to the n is just n-bit strings. So if we now, so if we are working over the space of n-bit vectors, sorry, and we consider k-dimensional subspace. What it really means is that since it's k-dimensional, we have a basis. And what we can do, we can just write this basis. Basis consists of k linearly independent vectors. We write them as a matrix, and such the matrix k by n binary matrix will be called the generator matrix of the code. So rank will be k again, k linearly independent vectors. And now we will define the code C as simply all possible vectors that can be constructed, well, that this basis will generate. So how it can be done, you just consider all possible k-bit vectors, and then if you multiply m by g, it will be vector by matrix multiplication. You will get all possible code words, and you will have 2 to the k possible code words in this case. So for example, we can take m as an arbitrary k-bit string. We have the 4 by 7 matrix. We have the vector 110, and then we will generate a code word as follows. We will multiply m by g as the equation shows, which will be vector by matrix multiplication. What you can observe is that the first bit of m is going to be 1, and therefore 1 will be multiplied to all the elements in the first row, and then the second element is 1. It means all the 1 will be multiplied to all the elements in the second row, and then you will see down there that you will have a code word x, which will be the first row plus the second row. Plus, in this case, is going to be a bitwise OR. So we are going to add them together, and we are going to see 1, 1, 0, 0, 0, 1, 1. And that will be the code word corresponding to the vector corresponding to the vector 1, 1, 0, 0. So note that incidentally, the first k, so first 4 column of the matrix are going to be an identity matrix. This is so-called systematic form of the generator matrix of the code. So what it really shows is that we can obtain the original sequence 110 from the code word easily. So in this case, we can simply read it from the first 4 symbols. And in general, we would just have to solve a linear system of equation in order to get m. Okay, so very simple. Now, next, what I would like to introduce is the so-called minimal distance of the code. So we have, we say that the Hamming weight of the binary vector will be the number of non-zero elements in the vector. And then the Hamming distance between two vectors is going to be the Hamming distance of their subtraction. And over the binary field, subtraction and addition are the same. As you remember, addition is going to be a bitwise XOR. And basically, we have just the number of positions where x and the binary vectors x and y are going to differ. So that will be the Hamming distance between them. Now, the minimal distance of the code will be the minimal such distance between any two codes in a code. So finding it is going to be a difficult problem because we have these 2 to the k code words, and then we'll have to compare them together, and then we'll find minimal distance. Notice that since the if you stare at it for a moment or think about it or just believe me, the minimal distance of the code will be equal to the minimal weight of the code word in a code. So since the sum of two code words is also be a code word. So now we would like to look at the so-called general decoding problem. And general decoding problem will be the following. So first, generate a code at random. What it means is that get a random generator matrix of the code. That will be G. Now, if you would like, so now if you take M, any binary string M you like, get the corresponding code word, which will be X on the right, and then you add the low weight error vector to that. And we will discuss in a moment what that weight of the vector t is going to be. then you are going to get a result which you can consider a code word with errors. And I'll show you an example a little bit later, and I explain what that means. So a general decoding problem will be looking so at the input G, Y, and T, meaning you know the code, you know the code word with errors, and you know how many errors you added. So you know the weight of the error vector. Find the error vector itself. That would be the problem, and this is a general decoding problem. Why is it the case? Because once you have found the error vector, then according to the expression which is written in the middle on the picture, x plus e, you will just add e to the code word with error, and then you recover the original code word. So that is the problem of decoding. So upon receiving y, which is a code word with error, find what was the error vector. And that would be equivalent to find the original string m, because you will be able to recover x, and finding m from x will be an easy problem, as we mentioned before. So general decoding problem was shown to be NP-complete by Berlekamp, Macalise, and Van Tilburg. So the question is, we need the problem of decoding to be hard. And the question is how to choose the error vector so the problem becomes hard. The easiest way is to make the solution to that problem unique. So we need to make sure that the error vector that needs to be found is going to be the only one. So for that, we need the Hamming weight of the error vector to be smaller than the weight of any code word. However, finding the minimal weight of the code is going to be an NP-hard problem. So the issue would be to find a bound which would allow us to choose the weight of the error vector. And that problem has been resolved by Coffey and Goodman, and they showed that the minimum weight of a random minimum weight of the random code is going to be larger than equal to the so-called Gilbert-Varshamov bound, with high probability in n, where n is the length of the code. Okay, so I will skip the details here. So I will not introduce you the Gilbert-Varshamov bound in detail. What I will tell you in the meanwhile is that given the parameters of the code k and n, so given the dimension, which is called, yes, so given the dimension k and the length of the code n, it is possible to solve the equation written in blue and then to determine the d, which will be the minimal distance of the code. So the situation will be the following. The real picture will be a little bit different because in the Hamming metric, the code words look differently as compared to the two-dimensional space, but it's easy to imagine what's going on looking by the following picture. So we have the code words of the code, which are somehow spread over the space of all binary vector, of all n-bit vectors. And now, if we look at the weight of the codes, then the code word of the code C is going to take the weight between the Gilbert-Varshamov bound and the n. So what we have to do in order to make the problem the hardest is actually to choose the weight of the error vector little below Gilbert-Varshamov bound. So what will happen is that when we add the error vector to the code word, it will going to take the result which I before called y, and now I'm calling it c on this picture. So c will go somewhere in between of all the other code words, and this will be the hardest situation for recovering such the error vector. How to solve the decoding problem? The algorithm that is called information set decoding by Prange and its variants can be used. So let me show you the example. Remember that we were dealing with the generator matrix G, which is shown on this slide on the left. And then let us consider the example. So the code word would be 11000011, where the bits in blue will be the M, which we multiply from the left to the generator matrix. And now suppose that we are going to get an error vector. So error vector has a weight 1, meaning one error will appear in the code word. So we add them element-wise XOR. What is going to happen is that the corrupted code word, so code word with noise, is going to be 11000001. So what you can observe is that information set, that is the set of linearly independent columns in the generator matrix and in the corresponding code word is going to be intact. So what happens basically is that we were lucky and the error didn't hit the information symbols. So decoding is easy. Having y equal to, as shown in the first line, what we will do, we take a guess that the message M was 1100. So now we have to confirm that this was indeed the message. So we have to confirm that our guess was correct. It's easy to confirm it because what we do, we take our guess M, multiply it by the generator matrix, which is shown on the previous slide, and then we XOR it with the corrupted code word. The result will be 00010, which is the error vector. And how we know that? Because we assume the knowledge of T. As you remember, in the general decoding problem, we assume that the weight of the error vector is going to be known. Since we got what we expect, we got the error vector of the weight 1, we confirm that our guess was correct. So suppose that we were unlucky and the errors would hit the information set. Then, as a result, we would get something of the weight larger than T. It means that our guess was wrong. So now what to do? Well, there are many information sets in the code word. So there are as many information sets as there are linearly independent columns in the parity check matrix. So what we do, we pick another information set and start over. So that would be the idea. We just go again and again and again and again. We run this algorithm iteratively until we are lucky. And since the weight of the error vector is going to be low by assumption, eventually we will be lucky, and then our guess will be correct, and then we'll catch the error. Yes, so Lee and Brickel proposed some optimization here, but it is minor, so I will skip that for the moment. What I will do, I will just go for a very easy estimate for the information set decoding algorithm. I will just estimate the probability that information set has no errors. So what I will assume that the errors take values independently. Then the probability that a certain bit in the error vector or in the code word will be in error is going to be T over N. And the probability that information set has no errors will be the probability that there were no errors, so 1 minus T over N, and it should happen K time. So so since the error vector is chosen at random, then by independence, I can just multiply all those probabilities. So now, if the probability of the set has no error is shown in the first row, then in the second row, I have the work factor, which is going to be that value 1 over that value. Yeah, so it's going to be 1 minus T over N to the power minus K. And the work factor is going to be exponential in N if K is proportional to N, which is usually the case. So typically in most code-based scenarios, we have that K is going to be N half or 8N over 10 at most. That is the situation. Yes. There was a question whether I can share slides. Yes. After the lecture, I will share the slides with Professor Giri, and then he's welcome to publish them at the seminar page if he likes. Yes, I will share the slides. So, right. My point at this slide was that information set decoding algorithm, the running time of this algorithm is going to be exponential in the length of the code. Therefore, by choosing the length of the code properly, I can make the work factor of the algorithm to be arbitrarily high. Therefore, n will be you could consider n to be a security parameter in this case. Of course, this was just a very basic algorithm and very basic estimate. There has been some major advancement for this algorithm. It's a Stern's algorithm of 94. I would refer you to the survey of Engelbert, Overbeck, and Schmid for the history of the development. And the most recent algorithms are actually surveyed and used by Esser, Köbler, and Mai. Now, the question is the following. Okay, so suppose I convinced you that that decoding random codes is a hard problem. So if I have a code words with error and then the length of the code is chosen properly and the weight of the error is chosen properly, then it's going to be difficult for me to recover the code word with errors as long as the code is random. Now, in order to build the so-called public key encryption scheme, what I will need to somehow build in a key into this system. So I will need what the cryptographers called trapdoor that will allow a receiver to decrypt the message. So M will be a message, which will be just a k-bit vector that we are going to send. And error vector will be just a correctable error, which will be used at the encrypting side. But then the adversary will not be able to decrypt a code word with errors because the problem is hard. But the legitimate receiver must have some secret information to be able to decode. So for that, naturally, we will use error correcting codes, and we will simply replace random code with a code for which the error correction algorithm is known. So what we will be dealing with, we will be dealing with the so-called nearest code word decoding. So now the situation is a little bit different as before, because we need to have the error which is going to be correctable. So what it means is that we need an ability to correct an arbitrary pattern of T errors, and therefore by the standard argument in the coding theory, we need to choose the minimum distance of the code to be larger than twice the weight of the error vector plus 1. And that could be seen from the left side of the picture, the distance between suppose that D is the minimal distance between the code words, and then what must happen is that there must be at least T errors from the side of x0, at least T errors from the side of x1, and one must be a separation between them. But there is a formal counting argument for that. So, okay, as I mentioned, we need to replace a random code with efficiently decodable code, which is good, whatever that means. So good would be to have the minimal distance d as large as possible, because the decoding algorithm for random code has a running time which is exponential. Well, it's exponential in the length of the code, but also it is exponential in the weight of the error vector. Therefore, the weight of the error vector must be as large as possible for security purposes, and hence, as we saw on the previous slide, the minimum distance must be as large as possible. So the codes with a large minimal distance are good. They are commonly used in the coding theory. Unfortunately, there is a challenge here because we have lots of candidates which are good in terms of they have good error correcting capability. For example, LDPC codes, Polar codes, some type of the algebraic codes such as Reed-Solomon codes. But unfortunately, we need an extra requirement, which is shown next on this slide. And the extra requirement is that it must be hard to deduct an efficient decoding algorithm from a scrambled version of the code. So I will explain that in detail a little bit. As you remember, the adversary will be facing a decoding problem. So for the adversary will have to know the code, as you remember in the description of the general decoding problem. Therefore, the code must be scrambled somehow in order for the adversary to be unable to get an efficient decoding algorithm, while the legitimate receiver will know it and will be able to decode. So some of the candidates, there were many candidates to be considered, the ones above and many other codes, because the topic of algebraic coding theory has been studied extensively in the past decades. And some of the candidates which still remain in the game are GOPA codes, amazingly as originally proposed by MAKAUT. More general class, which includes GOPA codes, algebraic geometric codes, as shown by Janua and Moreno. Some generalization of GOPA codes, such as Srivastava codes, and a certain variants of low density parity check and moderate density parity check codes, and some others. So a trapdoor. The idea by MAKAUT would be the following: choose G as a good code rather than a random code, and the public key will be a scrambled version of this code, and I will show you in a moment what this is. And secret key will be an efficient decoding algorithm. I think I'm running terribly out of time, and it seems that I have about 10 minutes left according to my counting. So please correct me if I'm wrong, but what I would like to do, I would like to give you as much introductory information as possible regarding the coding theory, so that you get a general idea what's going on here. And then in the remaining few minutes, I will just mumble through my recent results and the state of the art. So if you looked at cryptography before, you would see the basic structure of public key encryption on the slide. A public key encryption scheme is defined as triple of algorithms for key generation, encryption, and decryption. And the key generation outputs the two keys, public key and the secret key. They are connected. The public key is going to be available in the database, where the sender Alice would pick up the key of Bob, use it for encryption algorithm, and the input would be the public key and the message. The output would be the ciphertext. Ciphertext could be sent over the channel, potentially controlled by the adversary. Now the Bob will receive the ciphertext, and for decryption, he would use a secret key. So public key could be in the public database or on Bob's homepage, and that doesn't compromise the security of the system. So when the adversary intercepts the ciphertext and obtains the public key, as it's supposed to be known by everyone, adversary will still not be able to see what the message is. So I will tell you now, I will finish the story regarding MAKAUT's public key encryption, how it works, and then I will briefly go through the results that I wanted to present. So for MAKAUT's public key encryption, basically this is a kind of a high-level representation of the MAKAUT's public key. That's not exactly how it works in practice when you implement them, but it's kind of easier to see when you present them. So the secret key will consist of the random non-singular matrix, generator matrix of an irreducible GOPA code. So this matrix will have a specific structure. I will omit the discussion about that. And there will be also a random permutation matrix. So the public key itself will be a product of all those three matrices, S, G, and P. So effectively, S is going to be just a change of basis for G, and P is going to be a permutation, a random permutation of the columns. So public key, which I denote by gpub, will be S multiplied by G multiplied by P, which will be a permuted, effectively permuted generator matrix of the GOPA code. Now, how the encryption will work? The plain text will simply be a k-bit string. Is going to be multiplied by the public key matrix, and then the output, we take the output code word, and then we add a random error vector to that. The weight of the error vector will be t, and t will be exactly as mentioned on the previous slide. T will be exactly the number of errors that the code can correct. It's not mentioned on the slide, but that's the case according to the parameter. Oh no, it's written in red, sorry, yes. So G will be the code correcting T errors, and then exactly T errors will be chosen for the error vector. Now we got a code word, which is effectively, we've got a ciphertext, which is effectively a code word with noise. Now, what we can do, we can send this ciphertext over the public channel, and then the adversary will not be able to read the original plain text because the adversary is not able to decode random codes, and GPUB is going to look random for the adversary unless the adversary can run the attack. I'll mention that. Now decryption. So now the adversary, now the receiver, the legitimate receiver has a secret key. The secret key contains S, G, and P, and the decoding algorithm. So what the receiver will do, the receiver will first unpermute C, which by linearity, yes, questions? So
Hello. Yes, sir. There is one question in the question answer section.
yes.
Yes, sir. Sir, here the error is randomly chosen or any other thumb rule.
Yes, the error is going to be randomly chosen. That is correct. Yes. The errors here
Okay,
are
sir.
always chosen randomly. The random choice of an error is the part of the encryption algorithm. And they indeed need to be chosen randomly because otherwise, if the errors are not random, it facilitates the decoding. It gives the adversary extra information on how to correct errors. For the random errors, the adversary have no idea in quotes, and therefore it is harder for the adversary to decode. So I will go ahead now.
Yes, sir. Please go ahead.
Yes, the receiver will unpermute the ciphertext, and by linearity, we're going to have the M as G plus E multiplied by P minus 1. So it is going to be the error vector E. It will be permuted, but the weight of the error vector is still going to be exactly T, because this will be just a, so if you have an binary vector of weight T, then you permute it, the number of ones in this vector is going to be the same, and therefore we can use the decoding algorithm of the code to clean up the errors. And once we've cleaned up the errors, we decoded the code word, then we just solve the linear system and then we get the message back. That's the idea. All right. Now I'm going to, I wouldn't like to take some extra time, so I would like to very quickly tell you what's going on happens with the security of MAKAUT public key encryption. We have information set decoding algorithm as mentioned before. This you will try to run assuming that the code is random. There are also structural attacks which will try to obtain the decoding algorithm from the public key, because if you get the decoding algorithm, then you are in the same position as the receiver, you just know the secret key. Actually, such the structural attacks are known to fail, except for a very specific case of parameters where k is close to n. However, it is not typical for MAKAUT PKE, and therefore it can be avoided. So MAKAUT PKE is going to be secure, and from classic MAKAUT, I can show you the parameters. The challenge, as you can see, is the large public key. That's the common problem in code-based encryption scheme. So the public key size is going to be 130 kilobytes for the minimum security guarantees, and the key will be larger if you want higher security. 128-bit is a minimum security guarantees, whatever that means, yeah? So otherwise, the rest of the story will work. you will have to deal with some issues when you try to implement such the system. For example, for the internet security, the public key will not fit into one packet. Therefore, some issues can come from that, but they are possible to overcome. I will skip the rest. I will quickly jump to the discussion of the security of the MAKAUT PKE. What I will show is that the randomized MAKAUT variant is possible. So if you want indistinguishability against chosen plain text attacks, then you can do a very simple trick. You can deploy the random padding of the plain text. If you would like stronger security, such as CCA security, then Fujisaki Okamoto transform is recommended. That will require random oracle model. Some efficient construction exists in the standard model, such as the one by Matthew, Vasant, Venkatesan, and Rangan. It's an interesting scheme, but it needs some practical security evaluation. Yeah, so theoretically it seems okay, but for use in the practical scheme, the extra security evaluation is needed there. We also had a result about in CCA1 security of MAKAUT, but I will skip that. I am sorry, I will skip the story about cryptographic games, which are fun, but I don't have time for it. So I will go towards very end, and I will tell you that if you would like to have code-based digital signature schemes, it's interestingly turned out to be a challenging problem. No candidates survived the second round of the NIST competition. The wave scheme is an interesting candidate, but more research on practical security is needed. So if you really need signatures based on coding, then Fiat Shamir transform is an option, and we have an estimates about that. Future directions. We need to expand the range of advanced code-based cryptographic functionalities. We don't have homomorphic encryption of identity-based, practical homomorphic or identity-based encryption based on coding. Also, if you are an algebraist, you will find very interesting the alternative candidates for which were recommended by NIST in the third round, schemes based on rank metric codes. It's actually an area of algebraic coding theory where instead of Hamming metric, you look at the rank. Some other schemes, such as moderately dense parity check codes and HQC scheme is also interesting. It leverages some algebra mixing with BCH error correcting codes. Also, I'd like to mention that I will be editing an issue on cryptographic systems based on coding theory. So the deadline is March 8th the next year, and I invite you all to submit there. Thank you very much for your attention, and I'll be taking questions now.
Any question from the participant?
Yes, the nice question is there any connection with learning with errors problems in lattice-based cryptography? Yes. I skipped the slide, unfortunately. So if you look at the so-called learning parity with noise problem, it is a binary version of LWE problem. So if you just look at LWE, consider it over binary, you get LPN problem, which is equivalent to general decoding in the high noise case. So if the error rate is if the error rate is constant in the LPN problem, you will get exactly the same as general decoding problem. So they are closely connected for some parameters. If the error rate is low, then you get a different situation and different type of algorithms to break it, a little bit different constructions. But yes, that's a good question. There is a connection. Any other questions?
Sir, till now, no questions are further. And sir, we are waiting for hearing from ma'am. And
Okay.
Giri sir, are you there?
So, yeah. Since there is no question, then thank you, Kirill, for your valuable
Thank you.
speech. And hopefully we will meet again in our near future event. And thank you all. Thank you, Dr. Kirill, for your valuable speech.
Thank you for your invitation.
Okay, thank you. Now our next speaker is Dr. Garjia Marsan. She is currently working as postdoctoral research at the University of Brain